What's up, guys? This is Mr. Bond. Today we're going to take a look at antidifferentiation by substitution. So first, let's look at an integral that you guys can actually already evaluate. If I gave you this problem, you would hopefully just distribute the 2x to make the integrand a little bit easier to work with and then use some reverse power rule. But what would make this problem a lot harder is if I raise that binomial to the 50th power. Right, now we have an issue, because we can't actually expand that 50th power out. So let me show you a way that we can make this integral significantly easier using U-Substitution. I'm going to define a variable u to stand for x squared plus 1, and I'll talk about why I chose to do that on the next slide. I'm going to substitute u into my integrand. So now I have the integral of u to the 50th power times 2x dx. Okay, well, we have a problem here. We have u's and we have x's, and we need our variables to be consistent. So what I'm going to do is I'm going to observe the u that I defined on the right-hand side, and I'm going to actually differentiate it. So using implicit, du dx will be equal to 2x, and I can even just multiply both sides by dx and end up getting du equal to 2x dx. And commonly with these problems, people will just jump directly from u to du. So why did I do that? Well, look at the 2x dx. The 2x dx is in your integrand, and it's kind of the problem right now. So we can do a substitution where we replace the 2x dx with the du. So rewriting my integral, I have the integral of u to the 50th, replacing 2x dx with du. Now everything is in terms of u. And this is an integral that you can evaluate. So u to the 50th is just going to become u to the 51st power, and we need to divide that by 51, reverse power rule, plus c, because this is an indefinite integral. And we want to replace our u with x squared plus 1, just so that we can put it back in terms of x. So u becomes x squared plus 1 raised to the 51st, all over 51 plus c. And that is U-Substitution. So looking at that whole process, the one thing that kind of got it all started was me defining the u to be x squared plus 1. So let's look at why I chose to do that. So when you're picking u, you have a few different options. And this really is kind of like a puzzle that you're kind of putting together. Look for a function whose derivative is in the integrand. So for example, on the last one, we had x squared, which became 2x. If you see a composition of functions, look at the inside part. Functions that are raised to the highest power are a good option. And look for functions in the denominator. And more than anything else, just try something. You'll know if you got it wrong because the problem won't work out nicely. All right, so example 2. Suppose we have the integral of 4x cubed sine of x to the 4th dx. So trying to pick a u, we notice that we have a composition of functions with x to the 4th on the interior. X to the 4th is also the highest power in the integrand. And if we take the derivative of x to the 4th, we're going to get 4x to the 3rd, which we can see in front of the sine function. So my u is x to the 4th. Derivative of each side, we have du equals 4x to the 3rd dx. So doing the U-Substitution, I'm just going to be plugging in. Du is equivalent to 4x to the 3rd dx, and our function has 4x to the 3rd dx in it. So I'm replacing those two with du. I'll put that at the end. The sine function isn't getting replaced at all here, so it's still sine, but instead of x to the 4th, we defined x to the 4th as u. So now we have the integral of sine u du. And this is something that you guys can integrate. So thinking backwards, we want a function whose derivative is sine. So that's going to give us negative cosine of u plus c. And then finally, just substitute back in for u. We want to have in x to the 4th. We want everything to be in terms of the same variable that we started with. All right, example 3. The integral of x to the 6th times the square root of x to the 7th plus 5 dx. So immediately I'm pretty sure I know what my u should be here because I see x to the 7th plus 5 on the interior of that radical. So my du is 7x to the 6th dx. Now, there isn't exactly a 7x to the 6th in the integrand. So what I like to do for these problems is I actually isolate dx when there's not an obvious substitution. So dividing both sides by 7x to the 6th. And that way we can just plug in for dx. So going through it, we have x to the 6th times the square root of u times replacing the dx with du over 7x to the 6th. And what do you know? We have an x to the 6th in a numerator and a denominator, so the x to the 6th will cancel out, which is great because we want everything in terms of u, and now it is. That 1/7 we can keep out front as a constant, and you can actually extract that from your integrand, so we have 1/7 times the integral of u to the 1/2 du. Using reverse power rule, we know that we want u raised to the 3/2 power, and we want the constant out front to be a 2/3 that they offset. And we got to remember the plus c. And then finally, you can multiply your fractions and replace u with x to the 7th plus 5 again. And that's your final answer. All right, go ahead and try this one, and then you can unpause when you're ready to see the solution. All right, so what I'm going to do here is I'm going to identify cosine of x as my u, because cosine of x is on the interior of a composition of functions. So du is negative sine x dx. Now, I don't directly see a negative sine sine x dx, so I'm going to isolate the dx here, dividing both sides by negative sine of x. So I have du, which I can put the negative sign on top, over sine of x. Again, you don't have to do that substitution if you can see how things are going to fall into place, but it's kind of a nice process that always works. So sine x e to the u times, I'm going to substitute in for dx. So we have negative du over sine of x, and what do you know? The sine of x's will cancel out, which of course is going to happen because we know that it's going to end up being just in terms of u. The negative goes out front, and we have the integral of e to the u, which is the worst derivative rule and the best derivative rule. So we end up with negative e raised to the cosine of x plus c after the fact, and that's our final answer. All right, last problem. So for this one, I want you to try it on your own. Start by redefining cotangent in a different way. Okay, so the trick here is you have to redefine cotangent as cosine of x over sine x. Make u sine of x because it's in the denominator. Derivative of u is going to be cosine of x dx. Now, this one, we don't really need to get the dx by itself because we can kind of see that we have cosine of x dx pretty directly, right? So that's a pretty easy substitution for du. So rewriting my integral, the sine of x is really 1 over sine of x, and the sine of x becomes a u, so it's 1 over u. And that whole cosine of x dx just becomes du. The integral of 1 over u, you have to remember that's your natural log rule. So we have the natural log of the absolute value of u plus c, and then finally just plug back in for u, and that is your final answer. I really like U-Substitution because it kind of feels like a jigsaw puzzle that you know everything's just going to kind of fall into place nicely. On the homework that's attached to this asynchronous assignment, there are I think the first few questions that will just give you the u directly, so don't get thrown off on the first few where they literally will tell you what to use for you. All right, thank you guys.